So we're going to prove that n factorial is bigger than n cubed for every integer n bigger than or equal to 6. So we're going to do this proof by principle of mathematical induction. So we're going to do our base step first, and we are going to consider p of 6, right? Because that's our first one. So 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. And let's see, that's going to be 2 times 3, 6, 24. So 24 times 5. So 6 times 5 times, this was 24, so 20 plus 4, which is equal to 30 times 20 plus 4, which is 600 plus 120, which is 720. Okay. All right. So now we do 6 cubed. So that's 36 times 6, right? Because 6 times 6 is 36, and then times 6. So this is 30 plus 6 times 6, which is 180 plus 36, which is 216. And we can clearly see that 6 factorial is bigger than 6 cubed. So that checks out. Okay, so let's go ahead and move on to our induction step. We're going to suppose P of k is true. Thus, we will have k factorial is bigger than k cubed. Okay, so now let's go ahead and consider k plus 1 factorial. So remember, that's going to be k plus 1 times k factorial. And by assumption, k plus 1 times k factorial is bigger than k plus 1 times k cubed. Because by assumption, we know k factorial is bigger than k cubed. So k factorial is bigger than k cubed. And then this is equal to k to the 4th plus k cubed, right? All right, so remember, we want to show, so let's look at like what we kind of want to get. So k plus 1 cubed, right? Because we want to eventually show that k plus 1 factorial is bigger than k plus 1 cubed. So let's go ahead and look at this. So that this is equal to k plus 1 times k plus 1 squared, which is k plus 1 times k squared plus 2k plus 1. And then this is equal to k cubed plus 2k squared plus k squared plus 2k plus 1. And then that is k cubed plus 3k squared plus 3k plus 1. So we have to show that k to the 4th plus k cubed is bigger than this, right? Okay, well, I also know if k is bigger than or equal to 6, right? This implies that k cubed, right, is bigger than or equal to 6k squared. This implies that k to the 4th plus k cubed, right, is going to be bigger than or equal to k to the 4th plus 6k squared. Of course, equal to k to the 4th plus 6k squared, k to the 4th plus 3k squared plus 3k squared, right? So we're getting really close, k to the 4th plus k cubed bigger than k to the 4th plus 3k squared plus 3k squared. Well, clearly, k to the 4th for k bigger than or equal to 6 is bigger than k cubed. So you know this is bigger than k cubed plus 3k squared. And we know 3k squared, right, is going to be bigger than 3k plus 1 for k greater than or equal to 6, right? Because we can just do 6 squared times 3 is definitely bigger than 3 times 6 plus 1. Like, definitely. So we know 3k squared is definitely bigger than 3k plus 1 when k is greater than or equal to 6. So we've shown that k to the fourth plus k cubed is in fact bigger than k cubed plus 3k squared plus 3k plus 1, and that is equal to k plus 1 cubed, right? Because we did that earlier. So we've shown, thus, we have k plus 1 factorial is bigger than k plus 1 cubed, right? So assuming that k factorial is bigger than k cubed, we're able to show that k plus 1 factorial is bigger than k plus 1 cubed. Therefore, by PMI for every n contained in the integers where n is bigger than or equal to 6, right? We have n factorial is bigger than n cubed. And that's our proof by principle of mathematical induction.